Okay, now let's move on to multiple imputation. So the parameter of interest is quite general, right? I mean, estimating equations. And then, so on the no missing data, we know how to solve it, right? So the solution, so the estimator should be the solution to this estimating equation. So that part is no problem. And then we actually also know how to estimate the variance of the psi hat n. So subscript n emphasize that we use the n, no missing sample. And so then under some regularity conditions, we'll have a asymptotic normality. So that's just the general theory based on, so this is basically a central limit theorem. Now, unfortunately, we have a missing data, and that missing data complicate the problem. And so the multiple imputation idea is so originally proposed by Professor Rubin in 1978 and drew a lot of attention. So that's very genius idea. So basically through imputation using Bayesian. So that part is not really novel, right? I mean, that's quite natural. So you generate a parameter and then plug in to your model, imputation model, and then generate Y. So it's kind of two-step, right? You first generate parameter, and then second step you generate imputation. So that is quite natural. The novelty actually come from can be credited to point estimation and variance, especially variance estimation. So so the point estimation is that, okay, so the idea is create M, so M can be say 10, okay? So create 10 data set, 10 imputed data set. And each data set, for each data set, you compute basically point estimator and base. Okay. So for each data set, you compute the point estimator and its variance estimator, which is kind of a software, right? I mean, if you think about regression, for example, you have a subroutine already, right? So then you can just input the imputed data, right? And then you can obtain point estimator and variance estimator for each data, right? So okay, so you have a origin. So you have a one day. So this is you have a single data originally, okay, and then with imputation you create M imputation. So you're actually, so suppose you observe, so you have X and Y, right? You have a X and Y is missing. So you have some observation and then missing value here. And then idea is you can actually create 10 column of Y, okay? So you can create the Y1, Y star 1, Y star 2, something like that, right? So you can basically create the 10 columns. That means you can actually, you can view it as a creating 10 data, right? You have X and Y. So that is a imputation 1. So imputation M equal 1, 2, M equal 10 case, right? So conceptually, you can do this way. And then from each data set, you have a very nice, for each data set, you have a very nice, original data, right? I mean, you can treat it as an original data and apply this estimation method. And then from each data set, you can compute point estimator and variance estimator. Okay, so then you basically have a M pairs of a point estimator and variance estimator. So that's what step 2 is about. Okay, so you have a J equal to 1 to M. So M can be 10. I mean, for example. So you, and then since you have a 10 point estimators, maybe the final point estimator is just average. Okay, so that kind of makes sense. And then this part is known. So for variance estimation, you compute the average of the variance estimator plus this is what variance of the point estimator. Okay, so mean of the point estimator, mean of the variance estimator plus variance of the point estimator. So that's kind of an interesting idea. So that is very interesting idea, and actually, and also computationally, right? Computationally very attractive because the the users may not really familiar with all the technical knowledge in doing Taylor linearization and things like that, right? So then if you ask them to do linearize the variance estimator with imputation, they will be very frustrated. But this one, you don't have to, right? You just apply. So that's very computationally attractive, and so that actually is very popular. So, okay. Yes.
So the variance actually the variance of these inputted data sets and also the uncertainty in the parameters, right?
Something like that.
The variance in the parameters of the uncertainty in the parameters.
Right.
You are calculating that inputted values, right?
Right. So yeah. So actually, right. So when you apply, actually, I was gonna explain this a little bit. So in any missing, so in our, remember that our imputation estimator is actually function of eta hat, right? And then how to reflect the uncertainty in estimating the eta hat is actually key issue, and that's why we use linearization and application. And so this Bayesian approach gives another way of reflecting the uncertainty. So here's so let me first explain this a little bit on step 1. Well, this is I covered this already, but just to repeat. So the Bayesian imputation has a 2 steps in it. So the first step is we can call it posterior step, right? Posterior step. So which means that we generate parameter from the posterior distribution. And then a second step is actually imputation step, right? I step. So now that we have a posterior value, so now that we have a imputation parameter generated, so then here, so this one. So we have a parameter generated, then we can go ahead and plug in, right, to the conditional, I mean the predictive distribution. So then the parameters are all known. So then you can generate samples using some Monte Carlo method, right? So that's basically the 2-step approach for Bayesian imputation. The only difference from what we learned last time is that the last week is that we have a randomness in the parameter, right? Parameter estimator. While previously in the pre-contest approach, we don't do this randomness, right? We just plug in one. So plug in the MSA, MLE, right? So we can usually use MLE plug in here. I mean, so that means there's no, right? Plug in at the head and then generate. Okay. So then you might wonder, how come Rubin come up with this idea? Well, his idea is very simple. He came up with this idea, Bayesian motivation. So here's the Bayesian justification is really simple. So suppose you use complete sample point estimator. So remember, Pusai had n, so n is n, right? I mean, complete sample, no missing. So no missing. Suppose we can formulate the problem in such a way that my point estimator can be viewed as a posterior mean of the parameter given complete sample. So this is the means, no missing, right? So in this case, then the multiple imputation estimator is average. So point estimate, right? Point estimator, multiple imputation point estimator is the sample mean of the individual imputation estimator, right? And this individual imputation estimator is this one. So what is this? Well, individual imputation estimator is actually imputed value plugged into here, right? You plug in the imputed value to here. So that means what? That means your Y-com actually have a Y OBS and Y miss. So that means you are actually, so this is always observed, right? But the second term is missing. So you need to plug in to the missing part. So that's why we have this guy, right? We use this one. So that is unknown. So you need to plug in. So that is your case imputed value plug in. And then now let m goes to infinity here. Then we have approximation. So then this m goes to infinity, then it's just a sample mean, Monte Carlo mean. So it converts to the population mean with respect to the imputation distribution. So which is this one, right? So this is just a function, right? This is just function of y, and then you are basically taking sample mean, which is going to population mean for the respect to the imputation mechanism, which is this. So now once you have this one, then basically that's basically this one, right? This is the property of the expectation, conditional expectation. So conditional expectation, and this is the marginal expectation. This is the joint. So
Why you are suddenly using the capital Y?
which line? This one? Because y is random. Okay, that's good. So that means this expectation here is a expectation. This expectation, the second expectation, is with respect to y miss given y obvious and delta. Sorry, the first one. Yeah, right. Sorry. This one, right? The second one is just the posterior. So then the capital Y means that to emphasize that we are taking expectation with respect to Y. Okay, like this. Okay, so that is the first part. Okay, and now, do you need more time? It's okay. Okay, and then now let's move on. So, so first of all, this is a little bit so this factor 1 plus 1 over n will converge to 1. So we won't worry about this factor. So that's why we just use w plus b, and then and this is just the definition, right? Wm is sample mean of the variance estimator, and bm is the sample variance of the point estimators. And then if we choose, we had n, if you choose, we had n to be the posterior variance. Okay, posterior variance, then this one will converge to this expectation. The same way, if you choose psi hat n, right? So this guy is actually psi hat n. Y obvious, Y miss. Right? The inside expectation is this guy, and then you are basically computing this is the variance. So computing the conditional variance with respect to the f y miss given y obvious and delta. So this variance is with respect to
So I think we don't really need Bayesian if we can specify the conditional distribution given y observed and delta.
so y
So,
conditional
so there's no data in this distribution.
so
So if we already have the conditional distribution of y means given y observed and delta, then we don't need to put the posterior of there.
so your question is what happened to eta here? Is that
Yeah, because delta is integral.
yeah? So this one is actually this one itself is a two-step here. This one.
Can we divide the conditional distribution without the prior or posterior data? If we don't assume that data has a prior, so we still use this kind of imputation.
Okay. So well, so eta is the model parameter that is in this model, right? And then your question, is so are you asking the relation between psi and eta? Probably not. That's not your question.
And actually, we don't have data in this process.
Huh?
We don't have data in this process.
We do here. We have so we integrate out over eta. So how do you know this? And how do you generate the potential expectation. So this is the model. This is the actually integration. So you are taking the expect. So this one is actually from here. So we have a eta.
You calculate the second term in the integral being higher than A.
So right, we don't really. I see. So we don't really. It doesn't really depend on eta. Is that your? Because we integrate out.
I mean, can we directly assume that, no, can we directly assume a mode distribution of this, of y is given y of the, and the without knowing that?
So we can, yeah, so we can treat this as known, yes. Is that your question?
Yeah, can we assume a known form to this?
The form is this one.
So I mean, so we will calculate this from the prior line. So.
Yeah, prior, we need, so to compute this one, we need a prior.
So my point is that if we don't start from this Bayesian model, we directly assume that we already know the distribution of y is given y observed and delta n, and this distribution doesn't depend on era.
I see. So I see your point. So we don't really need a Bayesian imputation to justify this. It's that is your point, I guess, right?
Yeah.
Yes, I agree. Yes, but we do still need this assumption. So this is actually a strong assumption we'll see. So the first assumption is this one, and second assumption is this one, right? So we need these two assumptions in order to validate the Rubin's formula. But the computing the conditional expectation here, we don't necessarily need to use that Bayesian imputation. Yeah. Okay, that's good. So yeah, actually, so that is actually summary of the theory of Bayesian multiple imputation. So that is quite interesting because, Rubin developed multiple imputation in 1978, and he was a professor at Harvard, and he has a lot of students at Harvard working on multiple imputation, but they were not really able to give a theory, prove anything. So this is actually the work of the Wang and Robbins. The 98. So that was a biometrica. So this is two result is the work of Wang and Robbins. Robbins is not Rubin, totally different person. And so that's interesting because multiple imputation has been promoted a lot without real theory, serious theory. And so, so that was kind of mystery for a while. But later, these smart guys figured out theory. So we'll study this theoretical result today. But here's a summary. So basically, here's a summary of what I'm going to do. So, so basically, we want to show this, right? I mean, so this one, MI, because I had MI, multiple imputation point is made, and then this one is Rubin's formula, right? And which is a WM plus 1 plus MPM. Okay, that is we had MI. So And actually we need to and M. And we'll consider two cases. One is the psi is equal to eta. In this case, the estimating function is actually scope function. And case two is when we have psi is not necessarily equal to eta. So what is an example? So here's an example of the case two. So if y is normal, mu and sigma square, and the parameter interest is psi is less than y less than probability less than c, then maximum likely estimator is actually integration, right? Integration of the minus infinity c of the density function of y mu hat sigma hat square, right? dy. So that is the MLE because it's a function of the MLE parameters, model parameters. But that is, but there's another estimator which we can call it method of moment estimator. Right, method of moment is, so first one is MLE. MLE is of course efficient, but MOM is in this case is very easy and also robust. We don't really need so we can allow for departure from normality. So that's why it's attractive, right? In practice. So bottom line of the chapter 5 theory for chapter 5 is that in case one, MI works. So that means this property holds in the sense that the CLT holds. Okay. This one, case 2, does not work. So that is a kind of disappointing news to multiple imputation supporters because if it very quite limit the applicability of estimator, right? So for example, if I use MLE for multiple imputation, I have no problem. But for method moment, we have a problem. So by variance estimator is not unbiased, even asymptotically. So that is we'll see.
Jay,
Yeah.
may I
Sure.
ask for case one? In this case, the posterior mean converge to the MLE
Right.
of the obvious likelihood,
Exactly.
right?
Yes.
Okay.
So actually, case one, then right. So case one is a good news. Right? MI works very well, but it's not really clear why we do multiple imputation error if it's only applicable to MLE. But anyway, let's move on. So the theory, yeah.
So maximum likelihood estimation of psi hat for that is CLT will work or will not work?
Pulse.
In the second last line.
This one.
Okay, that holds, but if psi hat is probably y less than c, mu hat sigma hat square, then that is in case 2, right? Not in case 1.
So this one is a case 1. This one is case 2. So MLE. Okay. So the bottom line is MI works for MLE, but does not work for method of moment estimator. Okay. Not okay. So this is just two different estimators, right? But multiple imputation is not an estimator, it's a method for imputation. So you can apply to MLE. Also, you can apply multiplication to rest of moment. But the point is that theoretically, there is no guarantee that multiplication gives the valid inference when applied to method of moment estimator. Okay. So, so we are interested in asymptotic properties for multiple imputation estimator. So we'll focus on case one first for now. And so in this case, the imputation estimator is based on Serving's coequation. So that means by solving the imputance coequation for eta j, eta, based on the imputed data, J's imputed data. So theorem 1 is about point estimation, and theorem point 2 is about the variance estimator. Okay. So so let's investigate now. So let S be the scope function of eta on the complete response. And frequentist response, remember that frequentist imputation, we have a eta hat P. Okay, you have an estimator, constant estimator. And right, you have a constant estimator and solve this. So constant estimator to generate missing data, imputation, and then plug in, and then solve this for eta. So that gives a update, right? One step update of the so you have a better estimator of eta. In Bayesian imputation, we are not really using the constant estimator. We use from the posterior mean, right? And then there's actually interesting theory, sometimes called Bernstein von Mises theorem, which basically is a Bayesian version of the central limit theorem. Okay, so this is you can say that Bayesian CLT. So Bayesian, what does that mean? Bayesian CLT means that the posterior distribution, original posterior distribution is this one, right? Why? So this is a posterior distribution. I mean, we don't really need a star here. This is just a posterior. So this posterior distribution is converged to normal in distribution, converged to normal. But here, notice that we are talking about the distribution for conditional on the data. So then the point estimator so the mean is MLE, and variance is the information matrix, inverse of the information matrix. So based on Bayesian, you have already efficiency. So we'll assume this. So we'll use this one. So we are not going to approve this one. We'll just take it as if in an assumption and derive the theory. Okay. So in Bayesian imputation, instead of using a fixed eta hat P, we use eta star P. So star means we are generating. Okay, generating. But to emphasize it's a preliminary, we'll use a subscript P. Okay. So That seems to be quite difficult, but luckily we have a previous result. So the lemma 4.3 that we learned in last week, 2 weeks ago is this pre-condensed version. So if we have a fixed at type P for imputation, okay, and this at type P is converged to eta. Then the solution. So basically, what is this one? Okay, this one is this one. So that means what? You have a S originally eta and y, right? So you have a y . So that is actually S eta and y obvious and y miss. So you can write this way. So your complete sample score function has an observable part and missing part. And now since this is missing, you use imputed value here. Imputed value to here. Okay, imputed value. And then use that to solve it. Right? And then the updated one can be cancelled, can have this result, right? So that is what we learned already, what we started before. Okay. So we are not going to prove this again because we already proved it, but we'll use it, okay, to prove our theory for Bayesian imputation. Okay. So remember, the only difference is that we have a eta p star from normal eta hat MLE and I obvious inverse, right? From posterior distribution. So that's the only difference. Other than that, the structure is the same. Okay. So here's in Bayesian imputation, we use, so instead of eta P, we use eta P star from this posterior distribution. So that is basically this one. So the only change, if you compare 6 with 5, the only difference is that we replace eta P by eta star P. That's the only difference, and other things are the same. Okay. So, okay, so then let's think about what's going on here. Well, you have so remember here, the first term is the genuine, right? The most efficient part. And then this one is the extra variance increase due to using inefficient estimator. And this one, third one is the additional variance due to the randomness in imputation, right? So, and here it's the same story, right? We have a 3 term. And so this one, actually, here you can view this way. So this one, the first one is genuine one, right? This is genuine. Second term, you are actually creating a imputation, right? I mean, generating parameter. So you create the randomness from here. So this difference is the randomness due to step 1 of the imputation mechanism. So Bayesian imputation, remember Bayesian imputation, we have 2 randomness, 2 steps. Step 1, It's a posterior step, right? Step 2, imputation step, right? So this randomness is due to P step. And this guy is due to I step. So you have a MLE, but from MLE, you actually generate posterior parameter and add randomness with respect to the parameter. And then given the parameter, you generate missing data, imputation. That is the sort. So the 3 terms are independent because so conditional. So if you compare, so say let's use first A, B, C. Okay. So A, B, C are all mean 0, right? So A, B, C are all mean 0. And if you consider covariance, basically A is a constant with respect to the posterior step, right? So if you consider covariance between A and B, you have a 2 randomness. Expectation A, expectation B plus expectation of the conditional covariance. So actually the conditional. So what is conditional? So we are conditional on data. So conditional on data, then what is random? The randomness is generating the imputation. I mean, sorry, generating the parameter, right? Generate the parameter. So in that sense, so basically conditional on data, this guy is 0. 0 expectation, conditional. And also the covariance is 0 because this guy A is fixed, constant. Constant with respect to the posterior mechanism, posterior step mechanism. With respect to the randomness in imputation, this guy unchanged, doesn't change no matter how, right? You over the P step. So that's why we have A and B independent. This one? Okay, so yeah. So basically you eta star. So eta star P given data is eta hat MLE. Okay. So basically this guy conditional on the data is 0.
Data means the conflict data.
Right, data means this guy. So yeah, so I've been using yeah, so data. And the same argument that can apply to compute the covariance between B and C, because which one is more random? So you have so one thing is constant so because think about we have actually three randomness. Three. So let me so actually let's okay. Three phase structure. What does it mean? Phase one, you have a data, which is Y obvious. So data itself is a random variable, right? You have a data. And then given the data, you generate eta. So that's another randomness, right? And then third phase is that given the parameter, you generate missing data. You generate imputation. So Y miss star. That is actually F Y miss given data and eta P star. So that means, right? So then basically you have A. A is eta hat MLE minus eta 0. B is eta hat P eta star minus eta hat MLE times constant. C is Y miss minus so that is actually score function. So let's take a look what C exactly C is. Yeah, this one. So C is Y com, well, basically S com eta keep star given Y obvious Y miss star minus S obvious eta Y obvious.
Is just within the Australian mean is equal to the academic.
Are you talking about this one?
This one, the second one, yeah.
Second one? Okay. Yeah. So yeah, here we are talking about data is approximately equal to eta hat MLE. Yeah. Actually, this one we are talking about frequentist property. So this variance is actually frequentist variance, taking into account all three, the randomness in three phase.
This is the assumption we are assuming the Australian mean is equal to the
Huh? I'm sorry.
assumption.
This one.
No, the second one. Yeah, the assumption we are assuming.
Yeah. So here's that one comes from the 4. So Bayesian central limit theorem, right? Okay. Yeah, that I mean, let me see what's going on. Don't worry if you cannot really easily understand this, because even Professor Rubin takes 20 years to figure out the theory, right? So it's not really you are not alone. So okay.
We don't know the MLE, right? The MLE means what we could have if we don't have this in there.
Okay.
Or it's just.
Well, but still this derivation is valid.
Yeah, but the MLE, we don't know MLE in visualization.
But we do have a score function, right? We have a score function. So from the score function is actually MLE is we know the MLE will be solution to the square equation.
So it is from the observed data,
Right,
So
right.
it is calculated from the observed data.
Well, that's no different. I mean, so okay.
The notation for this eta hat family is not observed for
Observed.
not observed for
Yeah. Okay. Right. This MLE means the MLE on the with the missing data, right? Yes.
Mainly from the observed data, right?
MLE from the observed data, right. Yes. Sure. Yeah. So, right. Actually, that's a good point because yeah, it's a little bit confusing because yeah. So, right, because we don't really. I see your point. So in that sense, we don't really know the MLE on the complete sample, right? We don't know the MLE on the complete sample, but we only know MLE on the missing data. So and this one is the MLE on the missing data.
We can just compare it with lemma 4.3, right? So in 4.3, we use eta hat P.
Okay.
Why don't we directly use eta hat MLE, which may decrease the variance?
That's right. So that's really that's a good point. So the theory itself is nothing wrong, but that's actually very natural question. Then what's the point, right, of using all this when it actually increase the variance, right? So that is actually so see. So I will just show you the result for now. So the variance of the multiplication estimator end of the day has a 3 terms, and second term will of course goes to 0 if m is large, but m is not really large. Then you actually pay the price, so which is the additional variable. So variance is higher than MLE. So you're actually so if you can actually use right. So your actually your question is something like this: SCOM, why obvious? I mean, okay, why miss? And then you have data, right? Data and eta hat MLE, for example. So if you solve this equation, what you will get? The solution to this one the solution to this one is actually MLE. Okay, because so MLE will satisfy. That means you don't really improve further, right? So this is the best. So whatever you do, for example, if you use Monte Carlo sampling to compute the condition expectation survey, you are actually increasing the variance. You are adding the noise, right? Essentially. So this is the best, and there's no way we can improve it further. And so then why use multiple imputation to do all this? I don't know. I like to ask Rubin why. As I said, the idea is very interesting, but the usefulness is not really useful. I'd say. I mean, because you are end of the day, you are not really doing any better than just applying MLE, right? And it does not work for method of moment. Then yeah,
Jay,
yeah.
but the estimation of variance is very simple for
That's right.
multiple imputation.
Right. So that's a good point. Yeah. So point estimation itself is not really gain, but the variance estimation. So yeah, that's a good point. Actually, see the obvious computing this one is not really fun. you need to use, you did a homework, right? And once, and computing the this one is not, even using Lewis formula is not really convenient. But Rubin's formula actually gives an alternative computation, which is much easier to apply. So that's probably one real advantage of multiple imputation. Yeah. Thank you. Yeah, I think I agree. I mean, there's some good good use of multiple imputation, so should have an advantage. Okay.
Yeah, but Jay, I have so actually I have a question for. So if we are estimating eta, right? So we can use the posterior mean, right? So in your notes you have those 3 steps, right? So
Right.
next slide.
Right.
Yeah. So I think we can just stop at B, right? So if we get the eta star p, right? So we know that the mean of eta star p will convert to MLE.
Right.
So why do the 3rd step?
To get variance estimation easy.
Okay. 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 Good.
Yeah. So yeah. Anyway, that at least is have some interesting phenomenon. But yeah, for me, I'm not really impressed by multiple imputation. I mean, I was, but not anymore. So okay. Let's continue. So now, so previously this one is just a Bayesian imputation for single draw. Okay, for single draw. Now we have a multiple draw. Then in multiple imputation we have m draws. So then we can actually, so we can write it this way, right? You can still get the same decompositions, 3 decomposition A, B, C, and obtain independence, but you add up. You add m over them, average them over them. So then the 3 terms in 8 are orthogonal, as I said, and thus the expression 8 can be called the orthogonalization of the imputed estimator. So that is at least you can decompose. Basically, you first think about which phase, how many phases does it, so how many randomness in it, right? You have a so for this estimator, so this is an estimator, right? This is an estimator. This estimator has several steps in it, and then investigating the statistical property is not really easy because you have so many randomness going on. So then the trick is to orthogonalize. So this trick is actually useful because this one is a function of phase 1 sample only with mean 0, right? And this one is actually function of phase 2 and mean 0 conditional on phase 1. And this one is a mean 0 and constant with respect to conditional on phase 2. So that way you can orthogonalize, right? So you can, and then the variance decomposition is now easy to derive. Once you write this way, it's relatively easy to derive. Okay, so once you understand this 8, then the variance formula itself is should be clear. So basically here the variance of the MLE is this guy, right? And then the variance of this guy is that J miss is a kind of missing information fraction, right? I miss I come inverse, something like that. And then this guy is variance of OBS. So you have this one. And 1 over m because of you have m independent. And then third one, same story, right? You have this one and variance of the I miss. So that is this one. Okay. So that gives the complete theorem 5.1. And now, so this one is about point estimation. MI point estimation. So theorem 5.2 is about variance estimation. So the result is that Rubin's variance estimator is asymptotically unbiased for the variance of the MI estimator. So that is the result. And the assumption, so we have two assumptions. The first assumption is that the posterior values of the prior are generated from the normal distribution with mean, MLE, and variance. So that is the Bayesian imputation, essentially. The second one is that the complete sample variance estimator we had satisfies the ICOM inverse. So that means what? That means this is what ICOM inverse is the information variance on the no missing, right? If you have a no missing, then this is your, sorry. So this is your variance estimator. Variance, right? So under these two assumptions, we have a asymptotic unbiased. Okay, so I'm gonna prove. So we'll move on to this.
So Jay, can I ask a quick question?
Sure.
Does this require the score function to be the estimating equation?
Yeah. So this is all about psi equal to eta. So that means u equal to s. So
okay. Because what I'm thinking is that when psi equal to eta, we can choose other score functions. So if we choose other estimating equation instead of the score function, so this will not hold.
Right. Actually, that's what I'm going to cover next week. Yes.
Okay, thanks.
Okay, great. So okay, lemma 5.1 is that here the B term, right? If you remember, we had MI is a W plus 1 over M times BM, right? So this guy, we know that this guy in assumption 10 means that this one should converge to variance of the set at eta hat n. Sorry. Variance of the eta hat n. So let me quickly explain what's going on. So this guy is actually what? Variance of the eta hat n, where eta hat n is the MLE with no missing. Okay, so this guy is this. So remember, variance of, we are interested in estimating the MI, right? And we are interested in estimating the MI. And MI is approximately equal to MLE, right? And so that means we are actually kind of doing okay, and then do something like this. Okay, and so message is that this guy estimate this guy. So this guy is actually expectation of the W term, right? Because WM is nothing but the average of the V hat I. So So the W term essentially is estimating the complete sample variance. And so what we are eventually want to show is that this is estimated by BM. So if there's no missing, we have at M, but because of the missingness, the variance increase, right? And so the BM is because BM is the variance, sample variance, that is a positive, non-negative. So that actually adds some increase, reflects the variance increase. So that is the actually, so the theorem to prove 5.2, all we want to prove is eventually what we want to prove is this one. So that's the goal, but to compute this one, I need to do some algebra. So remember, okay. So now here, so this lemma is you have identically distributed but correlated. So not necessarily independent. So that means identical. So same mean and same variance, but they can be correlated. Okay. Then what is the expectation of the sample variance? Is actually sigma 11 minus sigma 12. So variance minus covariance. Is it clear? Probably. So let me briefly prove this. So how to prove it? Well, PM is 1 over M minus 1 summation equal to M xi minus x bar M square. So there I can because they have a M. Okay, so that why? Because you can always should be easy, right? So you can always do something like that. So there's no problem. So that means expectation of a BM is 1 over M summation expectation over minus M over M minus 1 expectation over x bar M minus mu square. Well, I think I didn't yeah. I don't know whether this is the best. This is one way, it's not necessarily the best way, but since I already started, I just finish. So sigma x, right? I mean, we assume identical. And then what? This is a variance, essentially variance of the sigma, right? So you can, what is this? What is this? This is m square over m times sigma square. So here actually sigma 1, sigma 1, 2. So this is actually sigma 1. This one is sigma 1. M times m minus 1, sigma 1, 2. Right? Because you have a, here if you think about, you have a summation, right? Summation. So you have a, you extend the summation and take the variance, and you have a variance part and covariance part. That's what you get, right? So then only thing left is just to simplify. So you can simplify, you will get turns out yeah, you can believe me and check at home. Actually, let me quickly give you another trick. So you can always, I think there's another way, much easier way. You can use this. This is another, right? Another identity. And then if you take the expectation, so expectation of BM is just expectation over x1 minus x2 square. That's another way. So I have only 1 minute, so let me see if I can. So that means our BM for applied to multiple imputation will be this, because sigma 1 minus sigma 1 2, right? And then what is this? So you remember using 8. If you go to 8, what is 8? We have a three decomposition, but the first term is common. First term is common, and second term, third term are independent. So that means when you compute the covariance is actually equal to variance of the eta hat MLE. And the variance term, you have 3 terms. Okay, so you have a variance of 3 terms and minus variance of MLE, so that you have these 2 terms, which is this one. So that gives this formula. I think I will stop here, and then we'll continue next week. Okay. Thank you.